Hello, everybody. Today we are starting Unit 2. You will find our notes on OMHS in the Unit 2 folder with today's date, 9/27, Day 1. Now, Unit 2 is a different unit than what you're probably used to. It's going to feel a lot different than any math unit you've ever done before. And that's just because it's a lot of definitions and a lot of logic. Well, it is logic. We're going to be using the logic that we're learning here in proofs and in justifying steps later in geometry. So we need to know these basic terms and tools so that way we could be successful in the future when writing proofs and whatnot. Okay, so if this unit feels different to you, all right, it's supposed to be a little different. Okay. So we're going to start by talking about inductive reasoning. Inductive reasoning is when you make a conclusion based on observations or patterns. So if every day I wake up, I take my son to daycare and I stop for coffee, then my 7-year-old daughter would assume that when she wakes up in the morning, we're going to get in the car, we're going to take brother to school, and we're going to get mommy coffee, because that is the pattern that we follow every day. And she would be using inductive reasoning whenever you're using a pattern or an observation and you make a conclusion based on that. Okay, so making a conclusion based on observations. There you are. Okay. A conjecture is the concluding statement that I reach using the inductive reasoning. So the statement that I make using that inductive reasoning, that's called a conjecture. So if I gave you the pattern, or we'll say pattern, square, triangle, circle, square, triangle, circle, square, what comes next? If you said triangle, then you just used inductive reasoning. And when you make that a statement, the next term in the pattern is a triangle. That sentence, that's your conjecture. So let's look at some examples here. It says find the next 5 terms of the sequence and then write a conjecture. So it says 38, 31, 24, 17. Figure out how are they getting the next number in the pattern, and then figure out the next 5 terms. Well, I'm noticing that to go from a 38 to a 31, minus 7, 31 to a 24, minus 7, 24 to 17, minus 7. So I must have to subtract 7 every time. Oops. So 17 minus 7, next term is going to be a 10. Minus 7 again, minus 7, minus 7, minus 7. There we go. So then we just write a sentence that describes that pattern that we just found and how we find the next terms. So to generate the next term, and maybe you word this slightly different, to generate the next term in the sequence, subtract 7 from the previous term. There we go. All right, how about number 2? How am I going to go from 2 to a 5 and 5 to an 11? Well, I know that 2 times 2 is 4. Well, it's not quite 5. Well, 5 times 2 is 10, which is almost 11. 11 times 2 is 22. I'm going to multiply by 2 and then add 1. So if I multiply 2 by 2, I get 4, plus 1 is 5. 5 times 2 is 10, plus 1 is 11. So we're going to multiply by 2 and then add 1. So 23 times 2, plus 1. Multiply by 2, add 1. And you can use a calculator to do this. I'm not doing this in my head. Okay, and then we would write a sentence. To generate the next term in the sequence, multiply or double the previous term and then add 1. So I'm just going to write that sentence. Okay, there is the sentence. All right, can you figure out number 3? What's the pattern in number 3? See if you can figure that out. I'm going to put the next few terms here and we'll see if we got it. Oops. $25, 36, 49, 64, 81. Did you notice that these are all perfect squares? So I could say that each term is the square of the term that it is, or is a square. We'll say is a square. I like that better. Each term is a square. There we go. To find the nth term, okay, nth meaning whatever term it is, square n. So if I wanted to know what the 14th term in this is, I would do 14 squared, because the first term is 1 squared. The second term is 2 squared. The third term is 3 squared, 4 squared. So if I wanted to find the 14th term, all the way out here, I would do 14 squared, and that would be the 14th term. Right, this one's a little different. Can you figure out this pattern? Okay. Here it is. The next term is M, P, S, V, Y, right? Hopefully you recognized that this pattern is skipping 2 letters after the previous term. So to generate the next term, and you could word this differently, but to get the next term, to generate the next term, skip 2 letters after the previous term. And if you needed to like write out the alphabet to do that, that's all right. All right, I'm going to let you do 5 and 6. Try them, and then once you enter your answers, we'll go over them. All right, number 6 was a tricky one. Let's look at number 5. Number 5, they were times, and each time was 25 minutes more. So I just added 25 and kept writing the times with 25 minutes added. And the conjecture, or the conclusion that I've made based on that pattern, says to generate the next term, just add 25 minutes to the previous term. Number 6 was a little tricky. If you didn't get number 6, that's okay. But each term here is a digit of pi. You know, pi, 3.14159, and so forth. Okay, so pi has these digits. So to find the nth term, you would find the nth digit of pi. Again, if you didn't get that one, it's not a big deal. Okay, so no stressing out if you didn't get number 6. Let's talk about what a counterexample is. A counterexample is an example that shows a conjecture is false. Oops, an example. Let me try that again. Okay, so this is an example that shows a conjecture, a statement, whatever, is false. Okay, it's showing that it's false. I like to call it counterexample, like your way to argue with me. Okay, and you'll see in a second what I mean by that. All right, so if I gave you the sentence, the sum of any two consecutive integers is always odd, you want to decide whether that statement is true or false. And as soon as you find one example that makes that statement false, then you can say that the whole statement is false. Okay, so you want to think of two consecutive integers, 1 and 2, 2 and 3, 27 plus 28, 127 plus 128. Okay. Two consecutive integers, add them together. Well, noticing all of these examples I come with, all of these examples that I've come up with, every time I add them, I do get an odd number. Even 0 plus 1 is 1, and that's odd. So this is true. This is a true statement. Speaking of true statements, here is our attendance word for the day, true. The attendance word is true. Got that written down? I hope so. Attendance word is true. And number 1 just happens to be true. So since it's true, we can't write a counterexample. Let's look at number 2. The product of two numbers is always larger than either number. Product means multiply. So I want to find two numbers that when I multiply them together might not necessarily be bigger than either number. Well, what about fractions, right? I could do 2 times a half. The product of those two numbers is 1. 1 is not larger than 2. So that would be a counterexample. So I'm going to say false. And my counterexample would be this 2 times 1/2 equals 1. Maybe you think of a different example. What about 0? 0 times 5, that's 0. 0 is not bigger than 5. And this statement is saying that that product has to be larger than either number, and 0 is not bigger than 5. So either one of those could be a counterexample. Maybe you have a different one where you multiply two numbers together and that product is not necessarily bigger than one of the numbers that you had multiplied. All right, look at number 3. The product of two perfect squares is always a perfect square. So start testing it. Let's find some perfect squares. I know that 1 and 4, well, 4 is a perfect square. 4 and 16. 4 times 16. That's 64. Oh, that's a perfect square. About 36 times 64. Those are two perfect squares. 2,304. Is that a perfect square? Let's find out. Square root of that number is 48. That's a perfect square. So number 3 is true, and you could keep testing this and you would find that it is indeed true. Okay. Let's do some more examples. There we go. All right. The area of a rectangle is 6 meters squared. And the dimensions must be 2 meters by 3 meters. Remember finding area? We've got a, whoopsie. You have a rectangle. It says that the area is 6. So, and this is saying the dimensions have to be 2 by 3. What if it was 1 by 6? That would still have an area of 6 meters squared. So this 6 by 1 rectangle that I just drew, that's a counterexample. So even though the area is 6 meters, its dimensions aren't necessarily 2 by 3. So a 1 meter by 6 meter rectangle would still have an area of 6 meters. How about number 5? Dividing by 2 always produces a number less than the original number. Can you think of a number that I could divide by 2 and it's a number that is not less than the original number? How about negative numbers? Negative 8 divided by 2 is a negative 4, but negative 4 is bigger than negative 8. So that's false. That's a false statement. And how about number 6? We recently talked about vertical angles and complementary and what those things mean. It says vertical angles are never complementary. Can you come up with an example where vertical angles are complementary? Well, we know that vertical angles have to be congruent, and we know that complementary means they add to 90. So what if these were both 45-degree angles? Well, now they're congruent and vertical, but they are complementary. So this is another false. Okay, and you could say if the two angles are 45 degrees, then they are complementary, or if the vertical angles measure 45 degrees. Okay, I like to say that a counterexample usually makes the first part of the statement true, but the second part false. So in all of these, right, like in number 4, I came up with a rectangle that made the 6 meters squared true, but it broke the second part. In number 5, I came up with a number that was dividing by 2, but it's not less than the original number. I came up with some vertical angles, but they are complementary, so I broke that second part. Number 7, if a times b equals 0, then either a is 0 or b is 0. That one's got to be true. And the reason for that is if I try to multiply anything, two numbers together, and I want to get 0, then one of those has to be 0. It's true that they both could be 0, but either a is 0 or b is 0. So that would still make that true. Let's see, number 8. Two angles supplementary to the same angle must be congruent. So let's see, two angles supplementary to the same angle. So let's say that angle A and angle B are supplementary. And let's say that angle A and angle C are supplementary. Okay, well, let's make a picture. Let's say that angle A, let's say this is angle A, this is angle B, and this is angle C. Okay, so angle A and B, let's say A is 120. What does B have to be? Well, it has to be 60 in order to add up to 180. A is 120, what does C have to be? Oh, it has to be 60 to add up to 180. Angle B and angle C have to be congruent. And in my picture here, they're even vertical angles. This is true, and this is actually a definition that we're going to be using later in geometry. All state names have at least 2 syllables. Can you think of a state name that has 1 syllable? What I'm thinking of is Maine. It's 1 syllable. Squaring a number and adding 1 will always produce an even number. Squaring a number and adding 1. Let's square a number and then add 1. 100 plus 1, that's an odd number. There's a counterexample. This is false. And I would use this as my counterexample. Okay. So a counterexample is pretty much just a reason why a statement is false. If it's true, then you don't need a counterexample. Oh, okay, there you go. That's the end of the lesson. How about that? All right, we're taking this unit kind of slow to start on this day. Next class, we're going to talk about more logic things. For now, make sure that you do the attendance quiz and the exit ticket. If you have questions, of course, you're welcome to join me in office hours Tuesday at noon. Have a great day, everyone.